All right. So welcome to session 2. Is there anyone here who wasn't in the first session? I'm asking so I can tell you what we're going to do. So raise your hand. Welcome, 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 welcome. So we have kind of rules, and so I'm going to frame set. We're going to the unknown together to talk about the conceptual and maybe mathematical, quantitative things with the whiteboard, things where you need to draw a graph and interact. And we kind of ask people in the first session had these diverse topics, about 10 or 15 minutes each. The time is about an hour and 15 we have, right? By the way, we're in the Monk cellar, you know, Edward Monk. So I'm going to start with a little bit of physical comedy. It's very challenging to be here, but it was so much fun, I don't think I did. So the roles. So I'm a moderator. And that means my role is to get things done on time and also to translate. If somebody says something that I think can be translated to the other disciplines, I'll do that. And sometimes I ask you to write bigger or something like that. And it's interactive. There are questions in the middle, but sometimes they stop, sometimes they start. And your role is to be yourself, to ask questions, and to maybe even dare to come up. So I'm going to start with a song. The reason I do that is to get people laughing. When you laugh, you notice there's other people around you, and we know that social ties are critical for longevity. Do you know that? Yeah. What? Oxytocin? Yeah. So in the first session, we had something about the thymus involution. I'm just a T cell, and my story's seldom told, educated in the thymus. I learned how to defend my country, laying low, seeking out the poorer quarters where the other T cells go, seeking out those lymph nodes only they will know. What's your favorite organ?
Oh,
Eye. When I first came to the retina, I saw a lot of neuron cells all expressing, what is it, rhodopsin? But one of them had a nasty virus. Like what?
Pink eye.
What? Pink eye. Started replicating, threatening the whole organ. Pulled out my dagger. Did what a T cell has to do. Even though I am a pacifist. 9-9, 9-9, 9-9, 9-9, 9-9. Okay, that's enough of that. All right, so we're going to start now. Also, I get to choose. I'm going to start with an unscheduled guest, Mira. And can you introduce yourself and say the topic?
I'm Mira. I work on biology of aging, and I lead a group at the University of Sheffield. I currently mostly work on food advice, and I just want to talk about one thing, which is trade-offs, and then I'll relate this as well to mortality.
And how much time, Mira?
10 minutes.
10
5 minutes. 5 to 10 minutes.
No, so at least 10 minutes, okay?
So, trade-offs, right? So everyone has heard trade-offs, or if you're an evolutionary biologist, so that's how I was trained, then you know what trade-offs are in evolution. If you're more medically trained, it's like side effects. Like any benefit you gain, there would be a side effect. In the aging field, this has been very pervasive. There always has to be a trade-off, especially because the evolutionary biology has been so strong. So if you just draw a trade-off, because Uri likes the graphs, right? You would have trait A, the expression of this, just how much there is of this trait, and then there would be trait B, and they're negatively correlated. Yeah? So this can be lifespan, reproduction, that's the classic trade-off. So, and I just want to put this in the mortality framework because that's what we've just been discussing in the last session.
So hold on. I just want to stop so everybody gets it. So what you're saying is that if I'm able to increase trait B somehow, I have no choice but to decrease trait A?
Yeah.
Is that like hardwired into the organism?
In evolutionary theory, people would say, yes, it's hardwired.
So
I would argue, actually, we overemphasize this trade-off.
So, for example...
What are the units?
Yeah.
Unix is just a arbitrary expression, how much there is of it.
Frequency or cost of population?
You could say, in terms of, it's not frequency, it's just how much, because it's not fitness. So,
What's an example you're giving?
an example would be units of reproduction per time.
So how many eggs a
lifespan.
fly
how many eggs
lays?
a bird lays?
Oh, let's say you work on flies, right? So
yeah,
how many
flies,
eggs a fly lays along the lifetime?
Yeah, and if you
And
would
this
select
would be
on
lifespan?
if you would select on high reproduction, you get a response on lifespan. Yeah, vice versa, you get the same thing.
Okay.
Yeah, so there's a lot of evidence for this in selection. So if you do an experiment, you select on high reproduction, you see the cost in here. Yeah, actually, if you look and this has been
And Mira, I'm going to
overinterpreted.
stop
Is
again.
my argument.
Why should I care?
You should care because this has been overinterpreted, because at this meeting we've already had many people raise their hands and say, okay, that's all good and fine, all these longevity benefits you show, but where are the physiological costs? What am I paying by taking this drug, or what am I, right?
I see.
And this is coming in part because we're worried that we will do harm,
Yeah.
right? That's our worry if
Yeah.
you're a medical
Right,
profession. Sure. But in the biology of aging, it's coming also because
We have this disposable soma theory.
This is just disposable soma.
Yeah, so
theory,
there's an ingrained kind of belief that there has to be a trade-off. There is no animal that can fly like an eagle, swim like a dolphin, and run like a cheetah.
Yeah,
Right.
and this works across species, right?
Yeah.
So if you elephants and mice, you can put on this. It also works within populations. Evidence is quite strong. So if you do selection within population, you can get responses. Sometimes if you look at genetic correlation space, you can also find this. But, and this is maybe important, and I think it's quite important, if you look at this within populations, in phenotypic space, that's what we are doing if we're treating humans, for example. And an analog here, which is maybe fun, is just actually, Uri mentioned it, the amount of eggs a bird lays, yeah? And what we can easily do in birds is manipulate how much effort they're doing within phenotypic space. So we're not doing an experiment, we're not selecting, we're just adding the amount of chicks the bird cares for. We're just adding reproductive effort. We're manipulating this axis in phenotypic
Could you
space.
draw the graph of that?
I can
This
draw
is what's
a
called the
graph.
lac clutch experiment.
Yeah, so you have this standard sort of thing. The prediction would be if this is lifespan or annual survival. It's annual survival,
Annual
actually.
survival of the bird. These are like great tits
The
in a forest near
prediction-
Cambridge.
The prediction would be if we have often you have a control where you don't do anything. You have enlarged where you add chicks, and the birds respond by feeding harder, right? They do loads more effort. You can measure
So this
energy.
is parental investment.
Yeah, you can measure how many times they visit. You can measure how many energy they expend. The prediction would be, so this would be reduced, and the lifespan would be higher for the reduced. That would be the prediction, right? And enlarged would pay the cost. This is the classic trade-off example, right? But if you analyze this, we've recently done this across all studies that are there. There's actually no effect, and the effect is so small.
Hold on. So there's a classic drawing in evolutionary ecology books that you go and fool the birds and you put different number of eggs in their nest, okay? And now you ask, what's the annual survival rate? And it looks like this. No, sorry, this is the fitness. So how many chicks make it and fly out of the nest? If there's just a few eggs, of course, there will be few chicks. More eggs, more chicks. More birds, more offspring. But above a certain point, as everybody who has teenagers knows, there's parental investment. So the parents can't feed. What? No?
Depends how much digital devices you give them.
How many digital devices? So there's an optimum. This is an experimental perturbation experiment, right? And then you ask these great tit species, what's actually the number of eggs they make? And it's really in this range. That's a great success for optimality theory and evolutionary ecology. And so this is just more eggs, more offspring, and this is parental investment. And it's so accurate that it's actually a little bit off, and there's second order theories to actually figure out. So we assume evolutionary is optimizing. The question is, what is it optimizing for? And now you can figure out subtleties. But that's like what I know. So you tell me. Okay.
So Uri's right. So when this started like this, the explanation of optimality theory, the disposable soma theory in the biology of aging field, the theory fitted the data in places so well.
Yeah.
So also if you think elephant mice,
Right.
that makes sense.
Yeah.
That you think that trade-offs in normal phenotypic space, if we would extend lifespan of humans using a drug, there must be a massive cost, right?
Okay.
There must be something really bad going
Okay.
on. I'm arguing from this evidence that we now summarized in the birds again when we have way more studies, that this effect isn't actually so big as we expect. So we should not assume that trade-offs are there.
Got it.
The second part of the evidence that we've recently showed is that if you think of this sort of trade-off, we sometimes observe this, but you can also only sometimes only observe it in stochastic space. This is because if an individual, this is something we recently published, which is quite interesting. So if you imagine an individual being, this is the reliability theory based. So if you imagine an individual being based of these sort of units of physiology that can fail over time, but we now partition this into reproduction and lifespan supporting physiology, and now you hit this system with damage. You have some individuals in the population that will be unlucky and will have their reproduction hit, and their lifespan isn't hit by damage, which creates a correlation within stochastic space.
So
so you
this is
observe
very
a
important,
trade-off.
so I'm going to slow you down again, because I want to
that's
translate for everyone. It's one of my roles here in moderator. So what Mary is talking about here is this class of models that's from engineering called reliability theory. Because if you look at Ford cars, is year 1, 2, 3, 4, you get this survival curve that looks like organisms. And if you do the hazard curve of the Ford cars, you might think the Ford cars are like living organisms, right? So that got people to think that the reliability theory of engineers might be relevant to aging. And the reliability theory of engineers, like a car, it says that the car has these different subsystems, and they start failing, let's say at a certain rate, P per year. And when all of them fail, you die. This is about independent variables. By the way, Mire taught me this in the last meeting we were together, right? So I'm so grateful.
I don't take any credit for the model.
Yeah, who takes credit? Who takes credit?
Gavrilova.
Gavrilovs, right? From the 19...
they're from the University of Chicago, and it's, I don't know what the year is.
Yeah, it's
but
pretty early.
1990
Okay, so this is a really interesting model. It has really interesting predictions. Like, for example, very old organisms wait for the last part to fail. So probability of death at very old age is P. So the hazard curve saturates at P per year. So it has the saturation built into it. Like I said, people over 100 die, their probability of death about 0.5 per year. So that model has that. And what Miri, I think, what you contributed is to think about like different functions as like to have these modules, right? Mm-hmm. So I'm just trying to translate for everyone. So from this now you have an idea about trade-offs. So what's your idea?
Yeah, so if you hit this system with damage and you force a single unit of damage per time, you have some individuals in the population that just in stochastic space, they'll be hit in this reproductive unit and not in the lifespan because the damage is correlated because I force one damage of unit per time that has to hit on the system. If every unit fails in a stochastic space, they're of course uncorrelated. Yes, but if you make this like a biological system generates a damage per time unit, you generate a correlation between these physiological domains. So if you then would look at this population, you would see a phenotypic trade-off, but this is actually not necessarily saying that if you would manipulate one, let's say make the lifespan bigger, that then you would have a cost on reproduction. Yeah. Yeah, so that's sort of another reason why trade-offs might not be real.
And my favorite example, I think also from Colin, is that if you look at the worms, the reproductive span is shorter than their lifespan, right? How long, how many days?
Day 8.
What? Day 8 they stop. But if you do your lifespan extension after they stop reproducing, it still works. It works, and Colin showed that the dramatic end of the last session was that you look at the ones that are, the 75% have died, they're really old, and now you do this lifespan extending, basically get rid of death too, right, by a genetic trick. You extend life by a factor of 2. So very, very old worms. It's not reproduction. So there's not a trade-off here, because that's one way to think about it. You can extend life without hurting reproduction because you can do it at a very old age. Would you interpret it like that?
I have no clue how actually. I just experimentally found it. I don't know how to.
Okay.
That's why I'm asking you. How would you?
Yeah, that's what I'm asking you. So we have a feedback loop here. Okay, so thank you for Amira. Wait a minute, maybe more questions? Yeah, go ahead.
So one question I have is like, you put these eggs to the birds, but they didn't produce them themselves. So they didn't prepare their genome for producing or caring for that many animals, right? So in C. elegans, the major trade-off, for instance, developmental speed is quicker. You produce the first egg, it makes an extraordinary impact on the reproductive fitness. So that requires for the whole body plan and developmental program to be accelerated. So how is this, I mean, I get this, but like how does this test the sort of genome's intention of taking care of?
So it relates to what you tried to explain here. So what this...
But just repeat the question.
The question is, are you doing something artificial that the animals aren't prepared for or have evolved to sort of see, right? Or do? It's actually, the answer is the reverse of your question, because the theory is stating what they're doing at this moment in time is constrained by the cost of fitness by then dying quicker. So I actually haven't stated the obvious question, why aren't birds always producing twice the amount that they're currently producing? Because then obviously they would have more fitness.
Right.
The explanation is because then they would die quicker.
Yeah.
But actually there's not great evidence for this. It's just like correlational. Yes? Yeah. But it's very believable, because if we do experiments that extend lifespan, often we see a correlated response in the reproductive domain.
Right.
But this doesn't mean that you need the reproductive response to get the longevity extension, which you just explained.
Yeah. Like Rose in the 1990s took the last eggs and grew them, and he got in a few tens of generations, a 4-fold extension of fly lifespan, and they were very late reproduction. So that was a proof of the evolutionary theory that if you delay reproduction, you can delay lifespan, and they don't reproduce so well when they're young. So some experiments show the trade-offs, but not all experiments. So it's quite subtle. There was a question there, and also you. Okay, and then we'll go next. Yeah.
So I'm not an expert in evolutionary theory. It seems to me that a lot of the fitness was optimized for a world that's very different from what we're in today. The most likely killer was like starvation. Through most of evolution, most things were starving to death, and like just being bit by dogs or whatever.
Right.
So it seems like our immune system, all this is optimized for a world that's very different from today.
Right.
So I'm not sure. It doesn't feel like a trade-off to me that I take something that turns off my hunger. Like my hunger was designed for shit, I'm gonna die of hunger all the time. So like, how do you think about that? That is a trade-off. Like most people would probably live longer if they ate less, because they just can't. Like we evolved to have this hunger that's not rational in the environment we're in.
You already come from an interventionist sort of perspective, which is what I would say. I'm more inclined to say, okay, yeah, that's the direction we can maybe more safely go to than what we've been thinking about, dictated by evolutionary biology, right? So I'm just trying to say that it's not the case that there won't be trade-offs, I'm trying to say we shouldn't assume that the trade-off is there. And you've just given us another reason why that assumption might not be right.
Last question.
My comment was basically the same. I mean,
Okay,
we're not
so
in the
Nick?
same environment. But there's also
Same comment. There's also you. Who you?
I just asked about this trade-off. If reproduction and lifespan is sort of trade-off, is there any study showing that when you take off the gonads of the fertilizer and whatever the animal is, will lifespan
Increase.
increase if there is no reproduction?
Yeah. Can you repeat the question?
Yes. So the question is,
Hold on.
the question is if you
Well,
remove
let her
the.
finish.
Oh, sorry. Go on.
Some studies in statistic results in humans. If the first, the period, menstrual period is earlier, and you live shorter, and it is later, you will longer, and it's also related to where you live heat-wise. If you live in near the equator, your first period will be earlier.
Yeah.
So if we do not reproduce any longer without any gonads, we will live longer.
So repeat the question.
So the question is, if we manipulate reproduction, can we change lifespan?
There is no reproduction.
Do you know the answer?
Yes. So that's why it's been. If we manipulate reproduction, yes, often we manipulate lifespan. But this doesn't mean that if we're trying to manipulate lifespan, that there would always be a cost on reproduction, or that this is the explanation and the central trade-off in biology of aging, and that's what I'm arguing against.
I mean, the classic thing in worms is that you ablate the eggs, and you get one effect on lifespan, and you ablate the eggs and the ovary, you get the opposite effect of lifespan because there's two opposite signals. And there's the Korean eunuch study, where you cut off their testicles, eunuchs, historically, they live 20 years longer than equal social status royal family members. So it's a very interesting question. I'm now torn, because it's so fascinating. So why don't we continue? Yeah. We'll go with our heart. Yeah.
One quick thing.
Yeah.
So we did some competition experiments in the lab, right?
Yeah.
And so we compete all the aging mutants against all the wild type. And every single aging mutant loses against the wild type in a competition under food limited conditions. But let me just in your support say the opposite thing. We then did every other mutant in the lab and they also all lose. So the trick is every time you do anything to the genome, they get slightly worse at that particular gene, even if it doesn't at that particular competition.
Right.
Even if it doesn't actually extend lifespan. So you can easily misinterpret the data.
So what you're saying is that if evolution brings us to some kind of fitness mountain peak, the definition of a mountain peak is any direction I go down.
Yes.
So any change I make in a wild-type situation, like you said, where you evolve to, will tend to be deleterious. Even if it doesn't affect lifespan. So that's something we have to take into account. Vadim?
Just a quick question. So what is the explanation for this paradox that humans, over the last 100 years, humans seem to be developing faster? For example, the menarche starts faster, the replacement of teeth, like bone growth and so on, and yet we are longer lived, much longer lived. So
that speaks to my point, that we assume this trade-off is so strong because in places this evidence is so clear, but often this trade-off can be broken. And we knew this already. There's experiments that imply, for example, that the genetic correlation between reproduction and lifespan just breaks down.
Right.
It's not there. Right? But we assume that it's there. So I'm asked questions like, why is this trade-off not there? But I'm arguing as an evolutionary
that the trade-off is not there.
So evolutionary biologists would tell you, so me, 15, 20 years ago, would say, please, no, don't start manipulating your lifespan because you will pay the cost. In your
Wait, what did you study? Are you an evolutionary biologist by training?
Biologist more generally.
Okay,
I like biologists.
Okay, good. By the way, this is a danger, right? If you have a theory that's very strong, promulgated by very charismatic individuals, it's going to stifle the field. For example, Monod thought there were only repressors, because you had the lambda repressor and the lac repressor. And it took 10 years to convince that the ARDD is an activator for the arabinose system, because the dogma was so strong. Just to In many, many other examples, sometimes you have to wait till the professor dies before. So I think this is the case of, in evolutionary theory, there's several cases like that. What do you think, Vadim, about that answer?
I didn't understand exactly the answer, but I think the answer is not clear in this particular case.
Why?
Because we cannot assume that these two things are coupled. For example, my personal opinion that people develop faster and therefore they probably would live shorter, but they live longer for other reasons. There's two independent events.
I see. Two independent events, development and hanging on and not dying is two different events, modules.
Development and aging are two different events.
Yeah, so,
Okay.
so the arguments and why I think I'm not saying that trade-offs don't exist.
Yeah.
I'm saying we should assume that the trade-off that we see is always there and we expect the outcome.
Okay.
Because if we go back to the original system where this all comes from, and we look at the data, we don't even support in this single system that's the best system to study it in. These birds are in the wild, in their most naturalistic habitat. We give them extra work to do, and they don't die. So, right, there must be other things.
Okay.
Could this be what mechanism can solve, right? Like, if you're trying to talk about a trade-off in general, you don't know, but like, if you're talking about a trade-off of, in the bird case, it's probably calories plus nitrogen from the proteins, right?
Okay.
So you know what is being traded off, and that puts you on solid ground. With evolutionary trade-offs in aging, we don't know what is being
Correct.
traded off.
Correct.
And that leaves you open to be
That's right.
confounded by putting two phenomena into one
That's
phenomenon
right.
and things
Yeah.
like that.
So in this lack clutch case, it was clear the parental investment and you can measure it. You can see the birds exhausted, and there was mechanism there. But if you don't have mechanism, it's too general. You're not constrained enough. Okay, let's give applause. Thank you for improvising. And the next speaker is Ifan.
So I'm going to talk
Yeah.
about.
Why don't you introduce yourself?
So I'm Ifan. I work with Uri on aging.
What's your background?
So I have an education in both mathematics and biology, and I did experiments for my PhD, but I haven't done an experiment with Uri yet.
Do you have a black marker? Good.
Yes.
Okay.
Okay. So I'm going to talk about.
And how long do you need, Ifan?
Sorry?
How long do you need?
I don't know, 10, 15 minutes.
Okay.
So I'm going to talk about damage in mice. So I actually want to follow what Brian talked about in the previous session. We're looking for mutants that have what we call steeper survival curves. So what do we mean by that?
But why should I care, Ifan? Why should I care about your topic?
Oh, why should you care? So, like Nick introduced, we observe a lot of scaling survival curves, and that for us means there are some systematic perturbations that change the whole system. And because the system is so complex, it's very actually hard to, when in such a situation, to know what's
No,
really...
Ifan, I'm going to stop you.
Okay.
Just say in one sentence, what's the bottom line? Why we should care about what you're going to tell us?
What's the bottom line is we want to find the mechanisms that drives aging and differentiate it from we want to have the simple driver rather than the complex.
So you want to have to explore what is, like, biologically could be the upstream factor that drives a lot of aging-related changes.
Exactly.
Very retro. That used to be aging field in the 90s. Ross theory of aging, blah, blah, blah. Then it was abandoned. Aging is an emergent phenomenon. Now Ifan is doing a retro thing, right?
Cassette tapes are cool again.
Yeah, cassette tapes are cool again. Okay, yeah.
Okay. So the tools with which we want to identify the drivers are genetics, right? Because genetics are open. They're not hypothesis-driven. They're data-driven. So we want to look. So the data we're looking at are survival curves of mutants, and in particular in mice. So the type of data we look at is the shape of survival curves. So you have fraction alive that goes from 1 to 0. And let's say in wild type it looks like this. So people did a lot of experiments to extend lifespan of mice. So you could have an intervention that lives longer. So let's say you have a curve like this.
So what's on the x-axis?
So this is age.
Yeah,
So this may be like 2 years.
right.
This is like 2.5 years.
Okay.
And alternatively, so this is what people typically do. But we realize that, like Nick introduced, if you measure the shape of the survival curves, you can actually have more information. For example, what I draw here, maybe it's a scaling curve, and maybe there's another intervention. I'm going to use a different color.
Not red, though. Do like the,
Maybe blue.
yeah, because the red and the green are really light.
Yeah. Right. So the blue curve I draw is what we call a steeper survival curve. So it has, so let's use Ryan's metric, which is standard deviation divided by median.
Could you make it a little bit larger what you're writing? It's very obvious. Double it.
Right? So on this metric, the blue is smaller. And on medium lifespan, it's longer. So we're looking for mutants that behave like this. There are many reasons why we're looking for such mutants. One Uri mentioned is that we think these mutants should have shorter sick span. So not only they live longer, but the proportion of life they spend in health should be longer. And that's something that the aging field is generally interested in. So this is actually a poster that we're presenting. The poster number is 28. So if you're interested in this particular premise, come to the poster both today and on Thursday. But now what I want to discuss is actually another type of information that these curves can give us, which is that we think that these mutants are actually should be genes that affects damage removal. And if they affects damage removal, then if we follow these pathways, we may be able to identify what's the nature of those damage. So is that clear? So how do we quantify steepness? So what we do is that we just take the 25 percentile and the 75 percentile, and the distance between 25 and 75 is called the interquartile range. And then we divide the interquartile range. So steepness is T. So this is 25 percentile, this is 75 percentile.
Right big.
So this way, if you have scaling as in the black dashed line, you will have the same steepness. And also,
It's probably one over steepness, right? This is
right. Sorry. So this is 1 over steepness.
Yeah.
And we also are interested in longevity, so which is just the T50. And we look at the NIAIDP study of mice. Mice interventions are mostly pharmaceutical or dietary interventions. And we plot steepness on y-axis. And we plot longevity on, I want to make it bigger. The longevity here.
What do you mean by longevity? You mean lifespan?
T50.
Medium lifespan.
Okay.
Medium lifespan.
Okay.
And you divide it by the control.
And so the control will be here. The wild type will be here. And because this is an aging study, most of the points are here. So I'm not using the left side because if they are on the left side, they're shorter living and they are automatically not included in the study. So I'm bringing up some famous longevity interventions. For example, rapamycin. So rapamycin lives somewhere here. So what does this mean? It means that they have similar steepness as wild type, maybe it's actually slightly shorter, lower steepness, but they have longer lifespan. So that means they have a shallower but longer living curve. And this is not what we're looking for. Why, again, we're not looking for it? Is because we think that they actually should have longer sick span, and also because we think that what rapamycin does will be similar to calorie restriction, which slows down the pace of life. And that if you imagine life is like a rubber band, and you just stretch that rubber band. And that doesn't tell you what the damage is. It just tells you that everything in your body is slower. So what we're interested in is stuff that lives here. Let's say here, and here, and here. And so what are these data here? So what we found is that senolytics lives here. So, and this is consistent with where we found the SR model that Uri talked about in Omar's work, that we think one of the damage that drives aging is cellular senescence. So if you design a drug that kills the senescent cells, you live longer, and you are steeper because you are constantly removing the damage. Another type of drug that also lives here, but maybe here, is acarbose. And it's a drug that inhibits the breakdown of complex carbohydrates in the gut. So it reduces the glucose spikes you eat after you eat. And notice that it's actually very different from calorie restriction. For example, I talk to people who are not familiar with the aging field. I tell them maybe acarbose is an interesting thing to look at, and they say, what's different? You just eat less. But it turns out that it's actually behave very differently as rapamycin or calorie restriction. And all the antioxidant lives here. So for example, in the NIA-IDP, they tried green tea extract, and it lives here. Another class of drug that's quite interesting from this study is stuff that affects the vascular system, vasculature. Like there's a transgenic mice that overexpresses VEGF.
Here.
Scaling is here.
This is scaling because you don't change the steepness, just the longevity.
Scaling is here.
So these are long-lived and steep. What's the question? The question is here is...
So the question is, this is the data we got, and I'm interested in hearing feedbacks from you whether this picture makes sense to you, biologically speaking. Because what does this picture tell us? It tells us that the damage that drives mice aging are senescent cells, glucose spikes after eating, and vasculature loss of function. I'm trying to see whether I missed a class of drug.
But we already know that. Like, you are asking if the order is correct, you know, and if the effect size is correct.
No, it's different. So when you do longevity interventions, you look for that. This is focusing also on the shape, not only. So dietary restriction and rapamycin and metformin, they move here. Scaling. These guys make you long-lived and steep. Okay, so they're like different. And And there are also SGLT2 inhibitors here, and non-feminizing estradiol
17 alpha.
in males, because we know that estradiol in females is very protective, and after menopause, there's a big decline in female health and hormone. So all this tells a picture that maybe somewhere here is hiding something like senescent cells cleared by the immune system, like macrophages, and these guys protect the vasculature. So it could be the vasculature are like the roads for the trucks that remove senescent cells, for example. Yeah.
So combinations, right? So if you do senescent cell clearing, you
Yeah.
get a squaring of the curve.
Right.
You get steeper.
Yeah.
If you make extra stem cells, you get an extension.
Right.
that's flatter.
Right.
But
So-
it flies anyway, you can combine it.
Yeah.
You get both.
And also here, there's one combination, rapamycin plus acarbose,
Yeah.
and the answer is you get the best of both worlds.
They're both, exactly.
You get the best of both worlds because one is production or timescale and the other one is removal. Rapa plus acarbose. So this is the ITP study. So those that don't know,
Actually,
you can
it
look.
goes further to the right.
Rich Miller runs it. So this is a study where, first of all, they use genetically diverse mice, not just black 6. And they do it in 3 different universities in America. So you replicate the experiment 3 times. And they have 400 mice in the... It's a good statistics. And so it's like a very good database for thinking about these questions about shape and... Yeah, yeah.
Maybe I just want to talk about this figure. Maybe I'm a little bit picky. So this is because your research question is the damage that drives mouse aging, but however, your figure seems like the protective effects of mouse aging. So if you want to stick back to your research question, I think you need to flip your figure, the big one. That is not the content, it's just the presentation.
You're talking about a presentation issue?
Yeah. I talk about only the presentation issue. This is a fantastic work, so I like it. But it's just, if you go back to damage, I think you need to flip it.
Okay, thank you.
Thank you.
And then Omar. And then
I just have maybe a bit unrelated question about steepness of the curve and which is maybe not where you were leading the discussion, but do we know if what explains the steepness of the curve in all of these cases? Because the fact that the curve is so steep, it means that at some point there is mechanisms that switches on and causes rapid decline.
So the question is, what explains the steepness? Why the steepness is better? Is that the question?
No.
What's the meaning?
The question is the mechanism behind steep decline in the end, is that the same in all of those interventions?
Right.
It's more wondering what are mechanisms that drive in
Okay. So what are the mechanisms that drives steepness?
Yeah.
Okay. So
steep deterioration in function specifically.
So it's a very good question. So we think that actually there are multiple mechanisms that can give you more steepness. And we understand this using the SR model that Uri talked about. So in the SR model, we have damage production, damage removal.
Ifan, maybe for the interest of time,
Okay.
I'll stop. I'll just say, with the metaphor, when do you get organisms dying at the same time? When is stochasticity reduced? So in this picture with the garbage and the trucks, if you have more trucks, each piece of garbage stays around for a shorter amount of time, and there's less time for noise to randomize things. So in the limit of infinite trucks, it's deterministic. There's no noise. And that's why if you increase removal, you get steeper curves. And that's why if I'm thinking that these have to do with removal of damage, these have to do with production of damage, and therefore, according to senolytics, maybe damage has to do with senescent cells. Vasculature. Glucose spikes hurt the vasculature. That's why diabetes, you get heart attacks, retinopathy, and kidney diseases. So you build a picture like that. Yeah. Omar, did you have a question?
Yeah, you see interventions that increase the mean lifespan or median lifespan, but decrease the maximum lifespan?
How could that be?
How could that be? If it's very, very steep, let's move it a bit.
Right. So it's actually, the answer is yes, and it's...
Oh, like this.
Yeah, exactly.
Right, yeah.
So the answer is yes. They usually appear in this graph around here.
Okay.
So they are steeper, but they are not. They're slightly longer living, but then because they are steeper, the maximum actually got decreased.
Do they exist?
They do exist.
I just want to say it's really cool if we had a rectangular curve, because then all your friends die together with you. So imagine you live to here and all your friends are already dead. Or what a bummer, right? This is like what? Yeah, you could be friends with younger people, right? I mean, your cohort. Okay, let's thank Ifan for. Yes, but then let's go on with the questions.
Yeah. So I just wonder if you looked at the incidence of diseases from which animals die, because these are UMH3 mice. 50% of them die from B-cell lymphoma. If any of these interventions would affect this particular disease, you would exactly obtain a more steep curve.
Right. The question is about different ways of mice die.
So any organisms die, there's asynchronous aging in different organs, but in particular in model organisms like in mice, it's very extreme. Like 50% of mice die from one disease.
That's black 6, not these diverse mice.
Both black 6 and UMH3.
Yeah, so we don't have access to such data, but we have some indication that actually interventions can shift the cause of death. But it's very preliminary, and because we don't have data.
That's a good question. Anything else? More questions? Okay, so let's thank Ifan. We have, 30 minutes? That's great. So, are you ready? Okay, great. So we have Weizmann. Let's give her a round of applause.
So a little bit self-introduction. Well, actually, I just slept 2 to 3 hours yesterday, so I was thinking this was the opportunity I asked you guys questions. But it turned out it's not what I expected, but still I'm going to make it the way I want to.
So how many hours did you sleep? You said you slept last night.
Yeah, because apparently there was a club next to my place, and the host didn't tell me about that.
There's a club and that kept you awake? So you slept for 3 hours? So let's give her another round of applause. And you have the pen? Okay, go ahead.
So a little bit self-introduction. I'm Weizmann Wang from the National University of Singapore. So my education process is a little bit complicated. I get my bachelor in pharmacy, and then I get my PhD degree in biomedical science, but it's more like a public health. And then I went to a hospital working in obstetrics, but during this time I developed some skill of programming, so I went to my postdoc in School of Data Science, and now I'm working in longevity. So this is why I have this question is also from my previous job when I was in gynecology and obstetrics. So any surgeon here?
Surgeon, you say?
Yeah.
Surgeons?
Yeah, surgeons? Great, because I'm not a surgeon either. So.
What hospital?
Okay, but don't say too much, okay. So here is a typical cancer tissue you get from the surgery. So this is the typical pathology slide we will get from a hospital. I know this is very ugly. I'm not very talented in painting, but anyway. So here is the cancer, is the malignant part. And a good surgeon is always trying to cut all these suspicious spaces and leave a little bit of these normal ones. They are the good ones, they are happy. So when we are in the hospital, we are trying to see, okay, so I want to know how far we are from a normal tissue and become malignant. So our team made some research that we collected a lot of these slides, and we do IHC crazily, and then we collect the image data. And in the end, we are trying to get something like a scale. So this is the scale, and this is the malignancy. So as you can imagine, this part is the they're the fighting part. It's like, I'm normal cells. I don't want to be cancer cells. I'm really fighting. So you can see that it's not like a linear regression. It's not like a linear relationship. It's more like here. So they are normal and steep, and then they go into the point that they are malignant. So this is what I have been doing in the previous job, and don't ask me how we established this, because this is the formula provided by a mathematician, not me. I just provide these concepts. So this is what we are doing. But if we look at this figure, we will see that if you join the first one, that you will see that this looks very familiar. Why it is very familiar? Because this is like the chronological age. And this is the bio age. After I joined the Center for Healthy Longevity, I read a lot of papers on different clocks, biological clocks.
Wait, I'm going to stop because it's not clear to me, so I guess it's not clear for other people. So you're making an analogy between your previous work on cancer cells, and you got a certain graph. And now you're taking us to another world that has to do with aging. Am I right?
Yes.
Good. Very good. So now try to understand this graph. Okay. So x-axis is chronological age, and each point here is a different person.
Yeah, each point is different person.
And here is biological age, which you measure by.
This is the point I want to talk about.
Okay. Somehow.
Yeah, somehow. Yeah.
So it's believed there's a biological age inside.
Yeah.
Okay.
So
you say that chronological age you're young. And then suddenly, at a certain chronological age, you become old biologically. Is that right?
It may not be so steep. I think, according to my very amateur observation, it's more like this shape.
Okay. So with chronological age goes, the biological age is accelerating. So like we said last time, like Hemingway said, gradual and then sudden.
Not that sudden, but it's still getting faster and faster and faster. So I read a lot of papers on how people develop this biological clock, especially something like the epigenetic clock and proteomics clock. And we are always trying to...
biological age of the tumor or of the person?
Of the person. Now we are getting rid of the tumor.
Let's forget about the tumor. So
I'm not in cancer.
Weizmann, what she told us is her history. She worked on tumors. She got a curve. Now she's in aging, and she sees the same curve, more or less. No tumors. Okay. It's more a mathematical analysis. So by the way, just to think about theory, one beautiful thing is sometimes a mathematical idea, you can transport, like you understand something in one theory, then you go up to the space of mathematics, and then you can land in a completely different system and use the same ideas. Yeah.
Different ways of measuring biological age.
Yes.
To an evolutionary biologist, it would be change in your yearly fitness. One component of that is your annual risk of dying, and the Gompertz type curve you just drew is typically what you do see, although it does level out at the very old ages. So there's some justification for the curve you just drew using annual risk of death as your y-axis.
Yes,
so what you're saying is that the older you are, your risk of dying as a kind of proxy for biological age isn't linear, but it's dropping then expanding. Yeah.
It doesn't drop; it's exponential.
I mean, it's like at young ages it drops. Age 15, then you have deaths by stupidity, and then you have this, and then it actually kind of plateaus. This is the risk of mortality, and maybe we can argue about that. But so you say there's a basis for this acceleration. Yeah, and also, by the way, if you look at physiological decline, like for instance VO2 max, just want to tell everybody here, if you read in the textbooks, because of the work of Nathan Schock, the great aging biologist, it's a linear decline, right? Everybody knows that physiology declines linearly with time. But that's because he was basing it...
If you are trained or not.
Yeah, of course. Yeah, of course. This is because it was a cohort study, when you do longitudinal studies, you find out that it's actually also gradual and then accelerating. And that's a statistical error that's very important for everyone to know. When you do cohort studies versus longitudinal studies and you average, sometimes a nonlinear graph for each individual can look like a linear graph when you do the cohort studies. That's, demographers know that, systems biologists don't know that sometimes. Then you get all kind of claims like 2 inflection points in aging and things like that because of basic demographic errors. This is very important to say. But also, decline in an individual is gradual than sudden a lot of times, even in the classic like linear. Okay, but continue, please. Yeah.
Sorry, one question.
Yeah.
I would have thought a biological clock's not sort of normalized such that at a population level the biological age is equal to the chronological age, and so it would be linear for the population.
Yeah, that is the point I want to raise now, because this is more like what we observe in our in the reality.
This is what we know.
Yeah, this is what we know. However, when we train this model, and especially many models are, I cannot name 1 or 2. It's just many models.
Right, you train them like this.
Yes, when
as if it was like this.
Yeah.
Is that right, Vadim?
Depends on what you train.
Yeah.
Based on features that you train on.
So what do you mean?
You can train for chronological age or for diseases or for mortality. Those are different clocks.
Yeah.
Or for the rate of change. I don't know which one.
So the first generation clocks trained on chronological age.
Age.
And so you can say they had this kind of model inside?
Yeah, it's a linear.
It's a linear.
Yeah.
So that's you're
except
correct.
For development,
Yeah.
Except for the development.
Okay, except for development. Yeah. But then generation 2 clocks, 3, generation Z, alpha, they trained on different things that might intrinsically look like this. Is that right? Like.
Yeah, this is actually, I want to talk about this because our team is working on epigenetics clock, and we are using the algorithm of the first, second, third generation, or even I call the yin clock as the 4th generation. So even the 2nd generation clocks, it is trained by the risk of mortality. So the score actually comes from another cohort, having a much larger sample size, etc. So with follow-up, and they are trying their best to make it as close as this one. So this is a little bit tilted here because we know that at a younger age, actually, our risk of mortality is higher than, let's say, this is the age 5. So this is what I observed. And then we have a cohort in Singapore called SG90. So this is a cohort including people of the oldest old. So all of them are over 85 years old. So the median age is 88 years old.
Wow.
And the biological age from all these clocks was 71 to 83 years old. So you can see that they are, no matter which generation we are using, they are still younger. So one reason is that I try to explain for my paper, so don't be too harsh on me. So for our paper, one explanation is that if they are living so long, means that they may be healthier than ordinary people. Otherwise, they won't make themselves as this oldest old population, right? So, but the other reason why this is a significant younger biological age from this cohort, I think it's also because when we are training these clocks, we didn't really consider that this is not a linear regression. Of course, we're trying our best to make it non-linear, and we are trying to make it more and more steep, but still, it may not be enough. So this is actually why I thought this was a discussion, so I raised this as an open discussion with everyone. We are now, of course, we are longevity people, and we are trying to train new clocks. So my question is that how we can make our clock like as close to this real curve as possible.
How many make clocks like real aging dynamics, right?
Yes.
And so any comments or questions? Let's open it up.
What phenotype are you looking at? What do you call, what is the biological age phenotype correlated to?
So for me, our lab, we major use methylation, so DNA methylation, and we also have some biomarker data. And I also built models from the, let's say, frailty scores and hand grip strengths, etc. Still, currently, my work is major, because chronological age is really the most handy one, but I'm trying my best to improve my work. So I'm opening this discussion for C.
Are you measuring the clocks in lab?
Yes, Buffy code.
So thank you, Weilan. Let's give her applause.
Thank you.
Okay, one last question. We have a tradition of a question before we go ahead.
Hi.
One more question.
I'm a bit jet lagged. I just came from Portugal, but I would like to understand better what are you trying to predict with your model?
I'm trying to predict biological age. So from Asian data, well, actually, it's because I only have Asian data, but anyway. So
what are the parameters that are key in your model?
Currently in my model, this y-axis is still chronological age. So that's why I want to ask you guys, the experts in the field, as what else we can do to improve it, considering if we don't have longitudinal data, for example, the follow-up data to observe the risk of disease and mortality. So I wonder whether I can just make a random mass model and put everything in, but that doesn't sound to be very scientific to me, so I didn't do that.
Okay, we'll talk offline.
Weilan, thank you very much. Applause for Weilan. And do one last song before you do the last bit, okay? Ready? So some people think that old age is a disease. Let's say it's a disease, okay? But research shows that often the elderly are more at ease. Yeah. Subjective longevity, subjective well-being is at its max, and so is crystallized knowledge. And you don't have those sleepless nights about your grades in college. Aging, aging here and there. Aging everywhere. And now it's my pleasure to invite Josh for the last piece of whiteboarding.
All right. So thanks for staying to the end, everybody. I'm Josh Johnson. I'm an associate professor at the University of Colorado, the medical school in Aurora, Colorado. I've lived throughout the United States training variously at the University of Wisconsin and then Arizona State for my PhD, postdoc at Mass General in Boston, and the common thread is that I've always studied ovaries from the first moment I stepped into a lab volunteering in a lab where I squeezed eggs out of Xenopus frogs. And it's disgusting.
But put the microphone closer to your mouth.
And I moved to a mouse lab soon afterward.
Was it Mark Kirsten?
It was not. No, good question. Right. No, this was David Kapko at Arizona State. So my concept that I'm raising here is that in this aging audience, how can we get to really understand causality, giving many inputs that influence chronological aging and the impacts of aging and the years upon our bodies? But coming from a gynecology background or reproductive aging background, I am faced with this problem that impacts upon the ovary tend to influence aging generally. And we have heard even examples in this session about how there may or may not be trade-offs in reproduction and longevity. And so I'm going to spend my time with a very simple depiction of the math behind what I work on, and I hope that Uri will help by expanding this to realistic equations. But what we do is we are looking for ways to extend ovarian lifespan or ovarian function. And so for any intervention, I'll call it I, this can lead to the anticipated ovarian functional length plus the impact of the intervention, right? So this could be in years and
Can you draw a graph about this ovarian?
Sure.
Just to put everyone on the same page.
Sure. So
this is, of course, the first organ that fails.
That's right. And so at age We'll do age 13 and age 51 for the approximate median ages of adult ovarian function and loss of ovarian function. And the curve tends to go like this through the population of women. And I showed some data that
what's on the y-axis?
Cross-sectional data. This is age, and this is ovarian reserve.
So this is log number of primordial follicles, right?
That's right.
So you're born with 500,000, and when you go down to 1,000, and you know, Josh had this amazing talk today. 1,000. Josh had this amazing talk today where he modeled this as basically a random walk because the damage actually stops them from dividing, and when damage goes below a threshold, they can start going, and so you lose them at a certain rate. And the amazing thing that I liked so much is that when you go down to so few cells, so few eggs going out every day, that you have a chance to miss 7 days of ovulation. That's where your cycle becomes erratic. That's premenopause, perimenopause. And when you skip 12 days, that's menopause. And you get to that at this well-known number of about 1,000 follicles left. That's menopause, age of 50. But you got it from this curve. You could rationalize all those numbers because it's a very simple random walk model. So this actually a very nice, let's say, example of explaining much with little. Like the model has no right to be so predictive.
I can agree
of course,
with
doesn't
that.
mean it's right, but it's very elegant. And so, okay, so that's just the background.
Thank you very much. So an extremely simple model can give you this curve of follicle loss over time. And something we've done is modeled out, well, what would happen if you removed, and I'll use another color, surgically, a piece of ovary from this individual represented by the line. And so the ovarian reserve at the time of surgery would decline. I've removed a piece of ovary.
Why would you do that?
And because when you're young, that piece of ovary will contain many thousands of follicles.
Now, why would you remove an ovary?
So removing half of one ovary, you can cryopreserve that tissue.
Oh.
And only to return it later.
So you have, let's say, cancer therapy, and you want to keep the fertility.
That's the normal indication, and how the technique has been proven in terms of efficacy was to apply this to cancer patients.
Okay, right.
But the model that we published earlier this year is instead doing this in healthy women, freezing thousands of primordial follicles. So this has declined like this, resumption of ovarian aging, and then just before menopause, replace the tissue. And so after a certain percentage of loss of follicles due to handling, you put the tissue back here, and because it's on a log scale, the impact on the plot here is amplified, this person will gain some time here in years, delaying where she would have otherwise hit menopause. Go ahead.
I understand when upon the time of transplantation, the ovary will be younger because it was frozen younger. How long will the young age stay? Maybe it would, in a matter of a couple of weeks, would basically synchronize with the age of the organism.
Indeed, it's a function of the total number of primordial follicles that are present at this time.
What you're saying is it's not age, it's number.
That's exactly right. So I could, starting with 500,000 here, I can estimate in this plot that I'm going to remove 100,000, and we'll do it at age 40. And this isn't quite right, but it's making my point.
And then when you return it, let's say you lose some in handling. Let's say you still have 100,000. That's why it's higher here, right?
That's right.
If you hadn't removed it, this woman maybe would have had 50,000, 30,000, but you added back.
That's right.
But chronologically older, but the number. So that's a way to test whether it's age or number, and the answer is number.
That's right. And the performance of tissue in cancer patients behaves like this. It depended on number after a certain amount of loss. But go ahead.
It just depends on the fraction of the ovary removed. Yeah?
That's
so
right.
It needs to be like 50%. Or...
And all 50% of one ovary is tractable to surgeons, and all of this is available with like sliders online in an interactive model.
So you think that the number of... So the idea is to give health benefits of having more oocytes in women who would be postmenopausal. So the question is it the maturing oocytes that are giving the health benefits that you're talking about, or is it the primordial?
Growing follicles. You need primordial follicles around to provide a steady supply of growing follicles.
So it's like if you had a drug that would have women ovulate once every other month, that might have a similar effect?
That one survives to ovulate is mostly independent of the denominator that are growing it over time. Instead, I'm glad I have this captive audience to say the ovary is really a very efficient killing floor for follicles. You get rid of so many follicles, leaving that one remaining, that it's not as much ovulating less regularly. It's just how many are growing over time and how regularly they show up. Go ahead.
I was wondering if the premature removal of the ovarian tissue will accelerate the rate of depletion.
If you remove it too late and you don't put it back, absolutely. If you remove it too late, you're removing so few in that tissue, so few remain, that there's no real benefit to doing it at all.
What is like the approximate age
The earlier you do it, the better. Around age 25 seems to be optimal. And interestingly, because of the patient population that shows up interested in this, those women tend to be older, in their late 30s. And depending on their ovarian reserve, whether it's high or low, given indirect measurements, it may be worthwhile, and they could gain something like 4 years as late as age 38. But this gentleman's point about a drug, it's the same thing, right? Slowing the rate of loss, or there's a sense that maybe pharmacologically, Evelyn Telfer in Edinburgh has evidence that you may be able to boost the number of primordial follicles given a pharmacologic intervention. Please.
So is this procedure, it's complete ignorance, is this like a big deal, this transplanting follicles?
There are trade-offs and there are consequences to surgery that I'm going to get back to, because after all, my title here is confounders. Mm-hmm. So, however, the trade-off that's related to the duration of ovarian function is how many primordial follicles survive, right? If you lose 80% of what you took out, it definitely wasn't worth it, getting back to her question. Mm-hmm. But, approximately 40 to 50% survival of follicles is the worst case. And if you remove the tissue very early in life, like at age 25, you can lose 50% and still get 15 years of benefit. Please.
What happens if you do this reimplantation after menopause?
You would be faced with the symptoms of perimenopause and menopause, and your ovaries would likely reawaken and function, removing those symptoms. Would and removing those symptoms, and you'd be cycling again.
Do you think the benefit would still accrue?
That's where we're getting closer to the word confounders. I don't know. I know that the benefit short term, while the ovary was functioning, as long as cycles were normal, that bone health, adiposity, etc., would be likely to be protected. And these are all, again, confounders we're building towards how that would affect lifespan. Right?
So where are you taking us? What's the question?
So the question is, how can I ever understand how this delay, X related to the delay in menopause, given the specifics of this patient's intervention, how does that relate to extended lifespan? This was...
Wait, I don't understand. So can you explain again?
Sure.
Well, let me try to understand.
Sure.
You're saying I do an intervention and I'm able to delay menopause by 15 years. Yep. And what I want to see is whether lifespan will be extended, let's say, by 15 years.
By how much?
Or by how much? This is a hypothetical experiment, right? Because it's hard to think, but it's possible in principle.
Exactly.
Yeah.
Women who have the latest menopause tend to live the longest.
That's
but
right.
Can I induce this by delaying menopause prospectively?
Yeah, so women who have menopause at 40, median lifespan 78, and women who have menopause at 50, like 55, median lifespan 83, so that's the range. They have like 20 years extension lifespan, a few years menopause, but there's an effect, right?
That's right.
So you want to now consider this hypothetical experiment and ask, how can I ever know the answer, right?
That's right.
And what are the confounders you're talking about?
So first of all, the numbers Uri referred to are the delay, how lifespan relates to the timing of natural menopause.
Right?
The timing of surgical menopause, actually, having your ovaries removed very early in life, correspond to a penalty in shortened lifespan, right? That's more significant than the delay you get.
Why is that? Why is there a penalty?
This is my audience to ask. I'm fascinated by that. We
Okay.
assume that those outcomes should be the same,
Uh-huh.
but people have surgeries all the time, right?
Yeah.
Why ovarian removal
Uh-huh.
surgery should be so powerful? I'll go here first.
I mean, so your question is basically if your procedure, I mean, how you can, I'm sorry.
No problem.
How can you create a procedure that replicates this naturally occurring, like, extended menopause?
Yeah.
Yes.
And those variables that you are mentioning are like time at which the procedure is done, maybe you can put them in a DAG and direct a cyclic graph.
I was about to go there, and although I'm not very good at causal thinking and causal inference
right.
and all of this, but I could, and so mentioning
you
is
need to
it is
put a
good
little-
enough for
a
me
little
for
bit of
now.
order, no?
But before I go on to further questions, I want to frame this a different way.
Yeah.
There are laboratories, there are companies that my collaborator here that can perform this surgical intervention assumes that lifespan is the ultimate benefit. The point to doing this is to have women be healthier longer. The consequence is they'll be cycling longer and have to deal with menstrual cycles. However, the ultimate sell or justification for doing a surgery is that this will enhance lifespan, extend lifespan.
Yeah.
And
If you manage to replicate it like exactly, then
if it behaves if it matches what we see in the natural population or surgical consequences of surgical ovarian removal.
So this can be addressed in model organisms very easily. In fact, the study has been done when young ovaries were transplanted to the old mice, and because they are genetically identical, like black 6 mice, it's equivalent to what you proposed to do.
Right.
And the effect is actually, I think, if I remember correctly, there was a significant extension, but very, very small. And so I would, based on this, it would suggest that probably in humans would not be an effect.
Yeah,
Just
and
simply just
in some
because
ways, we have more control here because transplanting mouse ovaries, you have a sense of the median number of oocytes that ovary will have that you're transplanting based on the age of the mouse. But here, we can actually subsample the human tissue and know about how many thousands of follicles we're having.
The young ovary in the old mouse, it's a very extreme, the entire ovary.
Humans have menopause and mice don't, so it might be a difference there. Because the human woman might be, at disadvantage compared to mice after menopause.
Yeah.
So
Please.
Isn't this something that like a randomized clinical trial is designed to figure out?
I think so.
Randomize
Other than
confounders, and then you measure.
Other than the problem with knowing the absolute number of follicles in the ovarian tissue you're taking from that person, you can only indirectly estimate it. And so what I would say is that imaging techniques are coming that'll solve even that. But indeed, yes.
You just need a large enough population size that you're evenly sampling across the distribution of follicle number.
And having conversations like this one may lead to enough confidence that it should be done in other than people who are seeking out ways to extend their longevity, the sort of leading edge.
I guess I'm not seeing this as distinct as any intervention in terms of any outcome. Like you do this for estrogen replacement therapy for heart disease or whatever. It seems like it's exactly the same question, which is you have an intervention and you'd like to know whether it affects an outcome.
Yeah.
And that's something people have gotten really good at, and there's a whole up. So isn't that what you're looking for? It's like a clinical trial?
I think so, and other than, risks involved with having surgeries, and whether or not an intervention can be shown to be safe before you start the trial, right? I don't disagree. I can say that, how many follicles you have does correspond to later menopause, but it's not been shown to be causally related in people. The studies shown in mouse with ovary transplant, that's true. But for now, I'm an ovarian biologist, and I view the impact of the ovary on longevity to be somewhat confounded, right? That's why I thought it was worth bringing up.
Well, I think like when you're doing a clinical trial, longevity is not usually allowed to be studied. It's more of a disease. But I think with this, would this not increase fertility?
This is mostly in the years, post age 45, and what you're trying to do is extend things, say from someone who would have menopause at 45 to 55. Yeah,
Sure.
so it's post reproductive years.
You do this post-reproductive years, but you're proposing that if you did it or earlier on, it would have a greater benefit.
That's right, and limited impact on the remaining ovarian tissue in terms of your likelihood of conceiving.
Well, so you could have two potential benefits. One, you could have increased fertility, and two, you could potentially have increased lifespan. So you could just frame it as a study of fertility, which is very, there's lots of funding for that right now. People are very interested in that. But you could also collect lifespan data along the way. Like that's kind of how we frame studies at my lab in longevity.
Nice.
So maybe that's an angle. But then one question on the curve. So it's essentially maybe not exactly a half-life, but the more you have, the greater the decline. The more eggs, the greater the decline. Yeah?
Yep.
Okay.
And as you see earlier towards approximately 13, that's right.
Yep.
There's some debate whether
Log scale.
it goes faster at a certain age, but we were talking that it's not
Yeah.
clear, right?
Yeah.
It's a household knowledge for lots of people that the decline looks like this, and then at age 38 it starts going like this. That's what's called the biological clock sometimes. It's ticking.
And that's egg quality absolutely declines in the late
but
30s.
in the number, it's not clear
Yeah.
if the curve fitting. This going back to Nick's question about regression, it's not clear if having two slopes is better than one slope, you told me, because of the quality of the data. So that household fact might be a myth. So I'm going to end now because of time. Sure. Let's give Josh applause. Today at the pub, at the bar, I'm going to do something I do at every conference, which is a kind of guitar talk about this emotional and subjective aspects of science. After the conference, after 9 sometimes at the bar. So you're invited. And if you like the style of this discussion, I think science can have more things like this, where you have good ingredients for interaction. So let's take a nice deep sigh of relief. Thank you. Let's thank the speakers that dared to come up. And everyone who asked questions or just enjoyed it. And see you at the bar, I guess, or tomorrow.
And thank you, Uri, for facilitating this session. Just before you leave, I have 2 things to say that might be of interest to you folks here. Can we just have the screen? So I just want to wrap it up and mention a little bit of next steps. I mean, number one, thank you for all of you who showed interest. It was like a little bit of an experiment. We didn't know what to expect, and it's great to see that people are interested in the intersection of physics and aging, and that people like from both worlds, from the physics world and from the aging world, participated and got together. So the way I think about it is, in a way, with aging, we are facing an exponential challenge or an exponential problem in a way that aging is going up exponential. And I wonder if like a solution for this is like trying to get exponentially amount of talent into the field. And if you can, increase exponentially the amount of physicists that join the field, that might really help us to understand it. And that only has to be done for a few years, and we have enough people. Vadim, you want to say something?
Maybe to disrupt a little bit, but I just want to thank you for organizing this session, because this is really amazing.
Thank you.
I mean, this whole idea is a beautiful idea to bring physicists together. I'm not a physicist, but I just enjoy to be in that company and discuss like fundamentals of aging, because everything else that is discussed at the main stage depends on what we discuss here.
I agree with you. Thank you, Vadim, for the encouraging words. And I know this will not be the last one of those meetings, and that's why this next minute is going towards. So number one, for the people who have data, I think you should talk to more physicists, the people that you just meet here that you know now, but also, I mean, just do a Google search on your university in the physics department and engage them and ask them, hey, how would you analyze that? Because I always think physicists are very interested in solving hard problems, and aging is a hard problem. It's interesting, but maybe it's just not on their radar, right? They have so many other things and so many other interesting things going on in the world, they just don't see it. So if you have data, reach out to people. And I think it would be cool that in the future, maybe each science paper has like a small section on physics, or maybe at least the appendix, you know, and the results of that. I think we need more of those whiteboard sessions at the conference. It's been the first time for me to do something like that. I think it's been beautiful. I learned some stuff. I think one of the most interesting things we discussed was actually in here. I really enjoyed that. But then maybe for the future of all that, I think it would be great if we could get like 300 plus physicists into the aging field in the next 5 years. And that might be like large numbers, and that means reaching out to physicists in your university. I also think it means that we have to coordinate ourselves to go to those meetings, because I think it can be very frightening if you are the only person going to a new field or a new meeting, knowing not anybody else, right? But there are like a lot of physics for cancer conferences, physics for the life, physics for whatnot. But if we could maybe organize 2-3 people from our field to go to each of those conferences and get like a subtrack there, that might spike the curiosity of those people there. And I think that would be very helpful for the field, but also for other people. And then with the last slide, we're currently putting together a conference. Probably it's going to be 3-4 days on physics and aging biology. It's going to be in Singapore. More information on that will be released soon, but just maybe mark, for those people who are interested, mark the first week of March on that and plug it already, because it's going to happen. We're going to reach out to some of you. We're going to have like an open call on papers and posters and whatnot, but we really plan on like kickstarting this physics and aging biology, I wouldn't call it movement, but a branch of the aging field that is needed. And yeah, you're welcome there. So thank you very much.